motors. So I'm going to do a lecture introducing DC motors here, and then we're going to do some modeling of it also in this lecture. So we're going to introduce DC motors, understand how they work, and then do some modeling of DC motors in this lecture, which I won't finish today. I'll have to finish it on Wednesday. And then the next lecture will be on, so 4.4 is going to be on DC motor performance. So it's one thing to be able to model a DC motor and to understand how it works, but it's another to understand the sort of way that the performance characteristics are described and how they're characterized. So understanding the data sheet on a motor is something that I hope that 4.4 will help us do through actually modeling the test setup. So we're going to model how they characterize motors, the test setup that they use, and then we'll like build our own like fake curves. So it'll be fun. So, but I've actually found that most of the resources out there to describe motor characteristics are pretty sad. They don't describe really how they come up with the curves. You're supposed to just understand that, which is, to me, kind of, well, not helpful, I guess. So, we're going to introduce DC motors first in this lecture, and then performance characteristics, and then we're also going to talk about how to drive DC motors as well. So, and then your final lab in the ME316 lab is using DC motors, driving DC motors, measuring some of the stuff that we can measure about a DC motor. So it's cool. Unfortunately, we don't have everything you can measure, but you can measure some of it. Okay, so DC motors are commonly used in mechanical engineering designs as an actuator. So everything we're going to talk about is going to be thinking of this thing as having electrical energy provided to it to drive some mechanical system. Now, exactly the opposite way of doing things, where you start with the energy and you convert it to electronic energy, is a generator, and it works exactly the same way, just in reverse. So we're going to think about this in terms of the DC motor because I think that it's much more common for a mechanical engineer to need to actuate something than to harvest energy from something, but both of them are possible. I think that they both happen, and you need to be able to work either way. And you can sort of just think about all the stuff that we're doing here as being reversed for a generator. Great. So one more thing on generators. So like I have a generator for my freezer because I have a lot of fish and meat that I'd really be sad if it died when the power goes out, which it does every winter. So I have a gas-powered generator. So what it does is it takes an internal combustion engine and takes that energy from the fuel and turns it into mechanical energy, which turns the shaft on a generator, aka DC motor, and then you take the electrical energy that's generated then, and you use it to power your freezer, in my case. Okay, so DC motors are commonly used as an actuator. Products such as pumps, fans, conveyors, and robots use DC motors to convert electrical energy to mechanical rotational energy. There are two main varieties of DC motor, brushed and brushless. We're going to focus on brushed in this class, and I'll talk a little bit more about brushless a little later on in the lecture. If you understand the brushed DC motor, you can understand the brushless. The operating principles and the characteristics of them are different, but the basic idea is the same. So brushed DC motors emerged in the mid-19th century as the first device to produce useful mechanical work from electrical power. one of the fathers of the DC motor, the Benedictine priest, Anios, I believe it is pronounced Jedlik. Benedictine priest, right? Crazy. Seriously, it's pretty cool. Invented the key facets of the motor: the stator, the rotor, and the commutator. Roughly speaking, for a typical brush DC motor, current flowing through the wire windings of the stator, so something that's static, produces a magnetic field that turns the rotor. So the rotor turns, and the rotor is turning because it has windings of its own that have current flowing through them. The commutator mechanically switches the direction of current flow through the windings of the rotor to yield continuous electromagnetic torque. The best illustration I've seen of this is this YouTube video, and we're going to watch it for a second. I was like, could I draw figures and wave my hands and reproduce this? And the answer was no. This is a really beautiful animation, so we're going to watch it.
Find DC motors in many portable home appliances,
for a couple minutes,
automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil.
So, this background magnetic field, as they're going to discuss later, it can be provided by permanent magnets, but for most DC motors, it's actually provided by another set of coils. Okay, so, yeah.
Is this kind of like a magneto in a motor? You ever heard of that? Or is that the wrong name?
Yeah, I think yes. I think that this is the same idea. I don't really have a great understanding of what that term is used to describe exactly.
Yeah, nor am I. I just remember one time from like a shop class I took in high school, and we were looking at the magnetos. Okay,
it's probably very similar.
Oh,
yeah,
okay.
I mean, so the operating principle here is that there's a background magnetic field. So this north-south is the permanent background magnetic field that's created, but it could be coils too that are creating a magnetic field in a certain direction across that's stationary, and then you have a rotating coil in that field, and if you run current through that, you're going to induce a torque, and they're going to show you that, which is pretty cool.
The armature is connected to a DC power source through a pair of commutator rings.
So what they're calling the armature is another name for the rotor that we're describing.
When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards.
Pretty smart.
This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the
So before we go on to the next portion, it's super smart, right? If you didn't have that, if you always had the direction of the current flowing, without this commutator switching back and forth the direction, you would end up with a rotor that turned one way, and then once it got to the other side, it would go turn the other way. I just go back and forth, which is not very useful for a motor, usually.
Coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero.
Why is that? Why is the torque action near zero when it's in this vertical orientation?
Because the pull is exactly the same on both sides.
Well, it's actually so if we go back up a little bit here.
Oh, is it 'cause it's
When the
not-
coil is
That's where it's
It's
at.
farthest away in the middle, right?
Yeah, so the torque, the moment arm of this torque is from the center of rotation, which is here, right, over to this arrow. So that distance is large here, maximum here. As it continues to rotate, it gets shorter and shorter, right? The moment arm shrinks more and more. When it's vertical, the moment arm is zero, so the torque is zero.
nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor.
It's pretty cool how they can show that in the animation too. This is like, I can't reproduce this. Like, it's gonna get more torque
Here is the
and
trick
then
to
less,
overcoming
and
this
more,
problem.
and less.
Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a
smart.
motive force is always present in the system.
I swear people used to be smarter than they are now. They could do stuff like this.
Moreover, the more such loops, the smoother will be the motor rotation.
I was going to say about more.
In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be
So this is what I meant by that external field, the stator's field, doesn't have to be provided by permanent magnets. In fact, most of the time it's provided by coils of its own. And those coils can be connected to the rotor's coils in different configurations, and the rest of this video describes that and how there are different performance characteristics based on how they're connected. And I encourage you guys to look into that more. I think it's a really cool description of it. And I think that the other videos that they put out are great too. So, the illustration is just hard to beat. So, great job on the illustration. Yeah, so the brushed DC motor is still widely used despite its limitations, which include relatively frequent maintenance to replace brushes that wear out or clean and replace commutators. So those brushes are in constant contact with the commutator as it goes around and around, and they're going to wear out. I mean, they're spring-loaded, and they're going to wear out. So as they wear out, the material that is ground off of the brushes gets everywhere. It gets all over the commutators, so they can sort of foul the electrical connection if you're not careful. So you need to do maintenance on them, clean them, replace the brushes, which is kind of a drawback to using a brushed DC motor. Other disadvantages of brushed DC motors include their relatively large size, relatively large rotor inertia, heat generated by the windings of the stator and or rotor, and arcing that creates electronic interference for nearby electronics. So compared to some other options, so like the brushless DC motor or a stepper motor, there are also some other types, but especially those two, it has some disadvantages. Like the relatively large rotor inertia, you can't get away from that with a DC motor. You're going to have a relatively large rotor inertia. Those coils that are rotating around in the field, they're going to have some inertial effect too, right? You can't have that stuff rotating around without having it be some sort of mass that's rotating. So that can be a problem. They can be relatively heavy, and they can cause interference. So when you have these brushes that are changing on the commutator, you can get arcing, you can get these sort of electronic interference or noise that can affect nearby sensitive electronics. Depending on where you are, some environments it doesn't matter, but in some environments you might pick that up, it might disturb some measurement device that you have. So there are some drawbacks. The reasons they're still widely used include that they're relatively inexpensive, so about half the cost of brushless DC motors, don't require but often still use complex driving circuits. They're easy to model and are easily driven at different speeds. For these reasons, an additional reason emerges, they're relatively easy to design with. So they're still very, very widely used. I think that people thought that once the brushless DC motor came online that we would all be moving over to that, but it turns out that there are some distinct advantages to sticking with the brushed DC motor that were just listed. Brushless DC motors work on similar principles but require complex solid-state switching that must be precisely timed. So generally the idea is that instead of having these windings move around in a rotor, you have several windings that are radially oriented in the motor, and they put out a pulsed field at a specific time when the rotor goes by, and the rotor doesn't have to have the coil on it. You can have permanent magnets on it. And so the pulse timing requires some very precise electronics. So you have to have internal measurement of where the shaft position is. And then it has to have electronics that will do the switching of the power supply. And it's pretty cool, yeah.
Is that what they mean by pulse width modulation?
No, but we're going to talk about pulse width modulation when we discuss motor driving. So you can drive a brushed DC motor with pulse width modulation. That also applies to a brushless motor, but you can drive even a brushed DC motor with pulse width modulation. It's actually the preferred way. It's the best way. There's some caveats, but yes, it's the preferred way. It's the least expensive, most efficient way to do it. It used to be that it was much more difficult to do with pulse width modulation, but nowadays, no problem. PWM is the cheap and easy way to go. We'll talk more about that. It's really great. I mean, we're living in this golden era of like just cheap electronic stuff. Digital electronic stuff that we can program. It's pretty awesome. So, yeah, we'll talk more about it.
$5 computer.
$5 computers, yeah. I mean, it's just like, it's amazing.
That you can mail.
Yeah. Totally. So, we all could have been rich on Bitcoin, but we missed. Actually, we didn't miss.
No,
We had Bitcoin in Mt. Gox, and that went under and it got jacked. So I don't even like looking at what Bitcoin is worth right now because it makes me very sad because I would have a lot of money.
Yeah. There's also Ethereum too, that kind of took off too.
Yeah, I didn't get in on that one. I just got demoralized after the Bitcoin thing. I was like, oh, never mind.
As soon as I found out about Bitcoin, it was too.
Yeah. Okay, so I had a friend who's like a true believer in Bitcoin. He got in really early and is now super rich from it. And he was like, it's like, you need to get in on this. And I did. I got in on it, and then I just didn't pay attention closely enough. Or, I mean, I don't even want to say it. I was like blaming the victim. Somebody jacked all my... So I am unhappy about that fact. Somebody jacked it all.
Oh, they didn't do it?
Yeah, well, it was this exchange that had it, and then they closed down the exchange.
Oh,
So it was
yeah.
like you were like trading,
I know what you're talking about.
and then it shut down, and then it turned out, oh, there's a bunch of Bitcoin missing, and then it was like a Japanese company, and then it just sort of like people disappeared, money disappeared, Bitcoin disappeared.
Very nice.
It was great. It was great. So I kept getting these emails like translated from like the original Japanese like legal proceedings, and I'm like, I'm never gonna get any more of these Bitcoins. They're just gone.
Stay on it. You
Just
might
gone
get
forever.
more.
Yeah. All right. So here we go. Brushless are great. We're not going to talk a lot about brushless. There's another video, so there's a link if you click there to another video that shows the operating principles. It's very similar in a lot of ways, the same ideas, but there are different performance characteristics. There's a whole lot of stuff that goes into that. It's great because there's like no maintenance, and they can be lighter for the same torque and whatever. There's some really good things about them. We're not going to go into that. We don't have time to do brushless and brushed, so we're going to do brushed in this class, and then I think you guys will have a good foundation to do brushless if you want. A good introduction to the modeling of brushless is actually given in this thesis by Balderson. I found it's pretty nice. So if you want to look that up, there's a PDF online of it, and it talks about the equations that describe the operation and all that. It's a pretty nice job. So we have already explored a model for a brush DC motor in the first lecture from this chapter. That model assumed neither coil, sometimes also called the armature, resistance, nor inductance were present. That is, it was an ideal transformer model. A linear graph of a much better model for a DC motor is shown in this figure. This model includes a resistor and an inductor in series with the electronic side of the transducer. So this is a much better motor model than the one that we looked at before, which was assuming that it was ideal. In reality, there is some resistance in the windings, and so you can't have any wire without some resistance, but if you wrap a whole lot of wire, even if it's nice, high quality copper wire, it's still going to have some resistance if you go long enough with those windings. So there's some resistance, and there's also some inductance. When you start coiling up wire, you're going to get some inductance. And that inductance can play a role, especially in the transient response of the motor. It's a significant factor. So this is a much better model. We can also add things like the internal damping and the inertia of the rotor to this. So we can add, for instance, we could add some damping, and we could even add an inertia element to it. And in fact, we will do just that when we do our sort of big example. It's more than an example. It's really a very important analysis that we'll do, very detailed analysis that we'll do of a motor. And you don't have to include these in your sort of first crack at a motor model, but it's good to include them to get a really accurate model. So this is a pretty good model that we're going to consider in depth. So let's talk about motor constants. The motor torque constant, KT, and back EMF voltage constant, KV, are related to the transformer ratio, TF, derived above to characterize a brushed DC motor's response. If expressed in a set of consistent units, say SI units, KT and KV have the same numerical value and are equivalent to TF. So precisely stated, with consistent units, TF is equal to KV is equal to KT. this is the first aspect of DC motors where we're going to encounter the manual or the spec sheet. Okay, spec sheet in a manual. This is one of the things that's probably most intimidating to young engineers. We don't know what the hell any of this stuff means, right? It's like listing hundreds of different characteristics. Who knows what these things are trying to tell us? Probably the most important, though, is the motor constant for a motor. And we're going to learn a little bit how to unpack that, how to crack what these things are, what they mean. So, however, manufacturers usually use weird units like ounce inches per amp for the torque constant and volts per kilo RPM for the voltage constant. And if they're given in anything but SI units, so if that's the case, they won't have the same numerical value. So KT and KV will be different, which is just really frustrating. It won't be equal to TF. So when you look them up in the manual, it's not going to be in a form you can use directly as a transformer ratio, for instance. So if they're given in anything but SI units, which they will be, we recommend converting to SI for analysis, or at least a set of consistent English units where they're equivalent. So the procedure for SI then, so once in SI, we'll have something like this. So if you have it in SI, your KT will be equal to some numerical value X in Newton meters per amp, and KV will be equal to the same numerical value in volts per radians per second. So if we're given either KT or KV, the unknown constant, so the other one, can be found by converting the known constant to SI and then using this equivalency. I think whenever you're going to do a detailed analysis, using this SI for it is good. For a one-off calculation, and the reason the manufacturers aren't just being assholes. They do this because they think you're going to want to know how to convert a current to a torque in a specific unit. So they give it to you in a unit that they think you're going to want. It's the same with the back EMF. They give it to you in a value that should allow you to easily compute how much back EMF you're going to get given a specific angular velocity of your motor, which is often given in kilo RPM. So they're trying to help you, but I think that it causes a lot of confusion when you try to do a detailed analysis. So, okay, so I'm not going to go into this, but I just wanted to preview what we're going to do next time. So more than an example, we're going to do a very detailed model and analysis of these electromechanical systems from the lab. So these are DC motors, flywheels, there's some couplings, some bearings here, and we're going to look at the spec sheet for the motors. So I have here this just like stuff straight from the spec sheet, and we're going to interpret this, we're going to build a dynamic model, simulate what's going to happen when we, say, change the input voltage, and then in the next lecture after that, we're going to learn how to even draw the so-called motor curves for the system. So we're going to really unpack this DC motor and learn a lot about it. So looking forward to it. See you guys on Wednesday.